Welcome everyone. This is 𝗙𝗢𝗟𝗪𝗪 Basic Electronics. In this lecture, we shall discuss the band theory of the solids. So, before starting the band theory, let us recapitulate whatever we have learned up till now in the previous lectures. So, in the previous lectures, we discussed about the conduction of current inside a conductor, how the current conduction of current takes place inside a conductor. We defined various terms like mobility, current density, and later we try to find out the relationship between the resistivity or the resistance of a conductor with the temperature. So how the resistance of a conductor changes with the change in temperature. And at the last point of previous class, we try to solve some of the numericals related to the various parameters of the conductor. So here first we will try to look the practical values of the conductivity for the various materials. So here you can see in the list, the first material is silver. So the conductivity for the silver is 6.30 into 10 raised to the power 7, and the unit of the conductivity is Siemens per meter. It is mentioned here. Okay, and the conductivity in metals, the highest conductivity is of silver, 6.30 into 10 raised to the power 7, and the copper has a conductivity of 5.96 into 10 raised to the power 7. Aluminium is also having a conductivity of 10 raised to the power 7, order of 10 raised to the power 7. Iron, the conductivity is of order of 10 raised to the power 7, and for the stainless steel, the conductivity is of order of 10 raised to the power 6. So here what you need to understand that for various purposes in the electricity and for the connection, for the windings, we use copper. The copper is the material weight that we use. In spite of that, the conductivity of silver is higher. So as we know, the economics here uh, is the big consideration, because the cost of silver is much higher than the copper. So but the conductivity basically shows, if we have two wires, one of silver and one of copper, of same length, same cross section, then the losses, and we use for the same purpose, then the losses in the silver wire would be lesser than the copper, because the conductivity of the silver wire is conductivity of the silver is higher than the copper. But as we know, we need to consider the economic factors. So as we consider the economic factor, then in our household, in motors, in transformers, and all the windings, the copper is used, and it is having a very good conductivity, almost equal to the silver, and there is a very less difference, and it is cheaper than silver. Okay, so in some old fans you can find the aluminum also. And so this is about the conductivity of conductors, and we saw some of the practical values of the conductivity for the conductors. And here now you can see the conductivity of semiconductors. So these two materials are semiconductor. This is silicon and this is germanium. For silicon, the conductivity is of order of 10 raised to the power -3, germanium 2.17, and uh, these two materials are called semiconductors. The material which are having the conductivity in between insulators and um, conductors. Okay, and the insulators like diamond, glass, teflon. I think this is wrongly written. This should be 10 raised to the power -11, -12, or it is between -11 and -12. This should be -11 again. Actually the value is in between the actually the conductivity of diamond varies in between 10 raised to the power minus 11 to 10 raised to the power minus 18. So, and the glass, actually here we have written the approximate values because the conductivity varies in glass, teflon, and in diamond the conductivity is between 10 raised to the power minus 18 to 10 raised to the power 18. So actually you can find these accurate values on from the net and from some reliable sources, and these values are almost accurate. So for the insulators, we need not to bother about the conductivity value because they are not used for the conduction. Okay, and now one question arises that diamond, which is a form of actually diamond, which is a form of carbon. It is a solid form of carbon, the allotrope of carbon. So it is basically it's carbon, and we know that the materials, and carbon is a group 4 material. Carbon is a group 4 material, 6, 2, 4, and the 4 electrons in the last orbit of the carbon. This is from some basic atomic structure we know, and in high school we have learned the atomic structure, and in a minute we will revise that atomic structure when we will start the band theory. And here the question is this: the carbon is of group 4, silicon is also from group 4, 14, 2, 8, 4, and germanium is also from the group 4. So actually the number of electrons in last orbit is 4. So these all materials are from the group 4, and but in spite of that we have classified carbon uh, as a insulator, and silicon and germanium as a semiconductor. Why? So in order to find find the answer of this question, we need to understand the band theory. So this is the motivation for the band theory. Why we need to learn the band theory? Because there are some explanations which can be given easily with the help of band theory, and like this. Here you can see these all materials are from the same group. In spite of that, we are classifying carbon, the allotrope of a carbon diamond mm, as a insulator. Actually there is a one more allotrope of carbon graphite which is having some good conductivity, actually better than diamond. Okay, so but conductivity is very low but better than diamond. So this is because of different molecular structure, and right now our question is just very simple. The diamond, which is a allotrope of carbon, the solid form of carbon, and why it is in the classification, why it is in the category of insulator, and silicon and germanium, which are also from the group 4, are in the category of semiconductors. Okay, so for the answer of this question, we shall look into the band theory. Okay, so let's start with the band theory. So in order to understand the band theory, first we need to revisit some of the concepts from the atomic structure. So let's start the atomic structure. As we know, by the basic atomic structure, there is a nucleus and there are electrons revolving around the nucleus in various orbits, and this is a kind of 3D diagram, and it is the 2D representation of the above diagram. This is a 2D representation and this is a 3D diagram. Okay, so as we know, the electrons are distributed in different orbits having different energy levels. So as this is from the basic chemistry of high school, we know that electrons are distributed in different orbits having different energy levels, and this energy is decided by the Coulomb energy, electrostatic energy K Q1 Q2 over R. So as we are moving away from the nucleus, energy increases. But here you can see there is a inverse relationship between 1 upon R. So how the energy is increasing? So the answer of this question lies in the negative sign of this energy, because we are talking about the energy of a system containing the protons inside the nucleus and the electrons in the orbit. So as the electron in the first orbit will have a lesser distance, then this value, the value of this kq1 upon r1 will be negative something, let us suppose negative 10. And then as the distance increases, this value decreases. Let us suppose this is negative 8. Let us suppose this is negative 8, and here the unit of the energy is electron volt, and for the electron volt I have already sent you the notes, and so you need to understand that electron volt from the notes. And in this lecture I will also discuss what is electron volt, but right now I am just taking it as a minus 10 minus 8, just for the simplicity I am not taking the units here. Okay, this is minus 10, and if we are moving more further, then R is increasing, and this K Q1 Q2, and here we are talking about for a particular electron. So if we are talking about the electron in first orbit, and the second, then third and fourth orbit, so the energy increases. Why? Because mathematically we know that if the energy is minus 10 and this is minus 8, this is minus 6, so which is greater? This minus 6 is greater. This minus 6 is greater. So here the sign also is of the significance. So this energy is greater. So as we are increasing, we are giving more and more energy. So if this is minus 10, then if this electron wants, if the electron in first orbit, let us suppose the electron in first orbit having the energy minus 10, and it wants to jump into the second, then it will have to gain plus 2 of the energy, then it will take a jump from this to this. So this is how we can understand that energy is increasing as we are moving away from the nucleus. So this is the bottom line of this explanation, that energy is increasing and force is decreasing. And the force is decreasing because force, for the force, the negative symbol is just the direction, and for the force the negative symbol is just the direction, and magnitude is decreasing. And let us have an explanation for the force. And the force of attraction between electrons are decreasing. For the electron in first orbit, the force will be greater, and for the electron in this orbit the force will be less. Why? Because force is again k q1 q2 over r square. This k is 9 into 10 raised to the power 9, and the constant, Coulomb constant. Okay, so this is the k q1 q2 over r square. So here you can understand the relationship between force and the distance. The force is inversely proportional to the distance. As the distance is increasing, the force is decreasing. Again there is negative, then this negative just signify the direction. And for the energy, which is a scalar quantity, the sign will have the significance in the computing the energy. Okay, so these 2 points should be very clear in order to understand the band theory. So these are just the 2 basics. As we are moving away from the nucleus, the force of attraction is decreasing. Force of attraction is decreasing between nucleus and that particular electron in that orbit. Okay, and energy is increasing. So these 2 points should be very clear. Okay, And now we shall move to the next slide, and before moving to the next slide, first we need to consider this electronic configuration. So as we know, in from the basic chemistry, the electronic configuration by this 𝗙𝗡𝗟𝗡's law, then 1s2 2s2, and we are taking the classical example of sodium, and this is the example by which most of the theories most of this band theory is explained. So definitely we will again take the example of sodium. So as we know, the electronic configuration 1s2 2s2 2p6 3s1. So here this 1s2, so 1 2 are the number of shells, s is the orbital, and this 2 is the number of electrons. So we need not to go into the details of that much chemistry, because we will just use the chemistry required for our explanation. And one thing that we have already discussed, and if further any concepts are required, then I will discuss it here. Okay, so now we know the electronic configuration, and we know the energy levels. So electron here, 2 electrons, 2 electron, and the energy level is increasing, and no quantum state can contain 2 electrons. So in these orbitals there are quantum states. At this energy level we have 2 quantum states, at this energy level we have 2 quantum states, and at this energy level we have 6 quantum states. So what do we mean by quantum states? So actually whenever these electrons change energy, if they change energy, they change in finite steps, quantums, because if an electron wants to move from this first one to second one, then it will have to, let us suppose for this first one, as we have discussed, and the energy is minus 10, and in the second one the energy is minus 8, and some unit of energy, and we as we have already discussed, we are not bothered about the unit of energy right now for the simplicity. And the energy at the first is minus 2, at the second orbit is minus 8, and again minus 6, like this. Okay, so if the electron wants to jump to the second orbit, so it will have to take plus 2 of energy, not more not less, and this is the quantum. So this energy, the energy required for the transition and for the state change is quantized. So a particular energy, so a particular type of or you can say a finite step is required to here you can see the step of 2. It's not like that these are equal and even steps. There might be uneven steps, but a step is required. If we are somehow by some external by some external source, by some lightning, by some heat, if I am providing energy less than plus 2, so it will not accept that energy, or it will not and it will not jump to the next orbit. And what happens if I provide less than plus 2? Then that energy will be dissipated as heat. Okay, so it will not make any transition. So for the transition, the finite steps of the energy required, which are called quantum. So here you can see and there are 2 quantum states. Here you have again 2, here again 6, and again 2 quantum states. Okay, so this is the electronic configuration of the atom. So and one thing you need to understand, no quantum state can contain 2 electrons. Okay, so for a quantum state, it can have a single electron or no electron. So this is the Pauli's exclusion law. And what you need to understand, that any quantum state can have only one electron. At the same energy level, we have here 2 quantum states. Here we have 2 quantum states, 2 quantum states, 6 quantum states, and 2 quantum states, and we are having electrons pertaining to those quantum states. But this is a Pauli's exclusion law, that any quantum state can have only one electron, okay, and it can be empty or having one electron. So this is the nature, and this is like this, okay. Okay, now we shall move to the next. So we have concluded two things from this slide. One thing is the energy, how the energy changes when we move away from the nucleus. When we move away from the nucleus, energy increases and the binding forces decreases. The attraction force between the electron and the nucleus decreases, okay. And the electronic configuration of the atom, the quantum states. So this we have discussed in this slide, okay. Now we are moving to the next slide. So here you can see the electron movement is possible in 3s state of energy. So this is related to a particular atom. Now before understanding this statement, what you need to understand, so this is related to one atom, but in solids we have atoms in the crystal structure. They are very near to each other, and whenever the atoms comes near to each other, when the in a solid atoms come together, the attraction with neighbors atom electron also starts beside the interaction inside the atom. So here we can understand the what is happening inside this atom, this nucleus, the binding, the attraction force and the energy level. And this is happening inside all the atoms. For this atom, the internal attraction is there, and this and this. And when these atoms are comes in the close proximity, when they come near to each other, the attraction between the interaction between electrons, the interaction between electrons and others, of the other atoms, the electron of this atom, electron of this atom, electron of this atom also starts. So this will create the energy redistribution, because the energy changes, because initially when we were discussing, the atom was completely isolate. So this we have discussed for the isolate atom, and this we are talking about a solid in which atoms are coming very close to each other. In a solid, atoms are coming close to each other. So in a solid, atoms comes together, the attraction with neighbor atoms electron also starts. So the attraction in the neighbor atoms also starts, the attraction between these atoms, this and this will have a interaction with everyone. So similarly for this, similarly for this, similarly for this. So the energy level changes, okay. So the electron movement is possible in 3s, and here what you can understand that why I am saying 3s, because the electron in 3s is the farthest from the nucleus, and it have the least amount of force. It has the because the electron in the 3s orbital, it is farthest from the nucleus, and the force between the electron in 3s state, the force between electron and the nucleus is the least, and that is why this electron is very that is why we can make this electron out of this atom very easily, just by giving some energy, by some light, by some heat energy, and by some other source. If we provide some kind of energy, then this electron movement in the 3s state is possible. And one more thing, that this 3s state has a one empty state, and this is also possible. From electron from some neighbor atom can jump here, and for a while it stays here, and then again it jumps from here. So this is also possible. So and the electrons, the interaction of this 3s electrons this 3s, the electron in the outermost orbital is very likely to happen. Why? Because the attraction force is least. The attraction force is least. So so this is how electron hops. Electron can hop, and these are the electrons which we call free electron, and these are the electrons which we call free electrons, because this electron is very easy to remove from its parent atom, and whenever we are applying some electric field, so this electron will be the electron that will respond to that electric field that we are applying. Okay, so now we shall move to the next slide. So when interaction is changed, energy level also changes. So this we have already discussed. So whenever we change the interaction between atoms, because initially there was only one atom we were discussing, there is an internal force by the nucleus and the energy levels, and now the many atoms are coming together to form a solid. So if the solid is formed, then those atoms are coming close to one another, and in that close proximity, the all those forces that a charge exerts on another charge is there, and the energy level is also there. So it when interaction is changed, the energy level also change. In some of the quantum states, this is some state, energy goes up, and in some of the energy goes down. So here we have these quantum states. This is a quantum state, this is a quantum state, and in some states energy goes down, and in some states energy goes up, and this affects the last quantum states in a very huge, in a very largely, this very largely affect the last quantum state. Why? Because here the electron is free to move, to interact, to jump, to hop, and to to respond to any external electric field. So this electron is free, and we have a empty quantum state here. So here, and for all those other quantum states are already filled. Okay, so in some of the quantum states energy goes up, and in some states energy goes down, and every atom is interacting with its neighbor. So here the basic of this all energy changes is this, that every atom is attracting to its neighbor atom. And here I have drawn a 2D figure. This is a three-dimensional figure. You have to assume layer one more layer, up and down there are various layers. So this is a simplified representation, 2D representation. So you need to understand, in a solid there is a 3D figure, and the atoms are there. They and at the bottom of this atom, there must be atom, and at above this atom, there should be one more atom. Okay, now inner electrons are not much affected by these interactions. So this we have already discussed. The inner electrons, these electrons are not affected much by these interaction, because the most of the interaction is in between the outer electrons, the electrons in the outermost orbit. So these electron participates in those interactions, and these electrons also participates, but the effect is very less. Okay, so next is this. So this is what really happens. When there is a interaction between the atoms, when the atoms come together to form the solids. So this the energy of this 3s, you can see the energy of this 3s changes. So here, if energy changes, and then what really happens, the energy bands are created at the 3s, as we know, this n, first you need to understand the number of electrons. This we are talking about the one atom. This we are talking one sodium atom. Let us suppose the example is sodium here, and we are discussing this all about one atom, but there are very large number of atoms. We know that by the Avogadro principle, the this n is order of 10 raised to the power 23 for a particular mass of the material. So this is n is this n is very huge. So let us suppose, and we have n atoms, then there should be 2n of this, because here at 1s we have 2 quantum states in one atom, and we have n atoms, there will be 2n quantum states, and again 2n, again 6n, and here only one quantum state is filled. Again here we have 2 quantum states, but one quantum state is filled. So these n states are now having the energy level changed. And why this energy level is changed? Because initially we are discussing the discrete energy level. The energy level is very sharp here, because we are talking about one atom only. But this is just for the understanding the theory of solids. So we consider one unit as one unit, and we try to understand the behavior of one unit. And then when we are forming the solid, then we will have to consider the interaction of units. Here the unit cell is atom. Here the atom is the unit cell. So we have as very large number of atoms which are forming the solid. So what you need to understand, here we have a very sharp energy levels, but when the interaction take place, this energy level changes, and we call these energy level as energy bands. So this is how energy bands form in the solid. So in solid we have energy bands separated by energy gaps. So these are the energy gaps that we have already discussed. If an electron wants to jump from here to here, then it will have to receive the amount of energy equal to this energy gap. Then it can jump from here to here. And if an electron wants to jump from here to here, so here from this 3s to this 2p, then it will have to release the energy equal to energy gap, and here it will have to gain that energy equal to energy gap. So that so this is the energy gap and energy bands. So electrons in uppermost band can take the energy and transit. So, and this is very likely to happen, that electrons in uppermost band can take the energy and transit. So these electrons can take the energy and can transit, and because they have a very less binding force with the nucleus. They have, and they are somewhere here there is a nucleus, and the binding force between these electrons and this nucleus is very less. And here and as we know, the energy states are there. So different energy states are there. So this is at a very higher energy state. So but this all is an entirely different theory. So what you need to understand here, these energy bands are formed because of interaction between those atoms. And for a separate single atom, we study energy band as a very sharp as a sharp levels. Okay. So now we shall move to the next slide. So these are the electrons that will respond to electric field and will move according to F equal to QE. As we know, the electric field exert a force on the charge, any charge, and that force is F equal to QE, and on electron it will again exert apply the force, and the electron in that outermost energy level will be the one that who will respond to this electric field. So here in this case, the electrons in 3s orbital will respond to electric field for electrical conduction. So this we have already discussed. Therefore this band is itself called conduction band. So this band is called conduction band because electrons in this band can respond to electric field, and they are free to move because they can break the connection to the parent atom by some external force. And if the external force is applied by the electric field or by the normal temperature, at the normal temperature the heat energy is imparted, and that heat energy is also sufficient to break the electron from its parent atom. So therefore this band is itself called conduction band. Okay, just a lower to conduction band known as the valence band. And what is valence band? Just lower to conduction band, the band known as the valence band. So these are the definitions related to the quantum mechanics. Okay, or you can say the atomic structure or the valence and the band theory of the solids. So what we have concluded, basically if we have a separate atom, then there are sharp energy levels, and we know the energy levels are there, and there is electrons are distributed in different orbits, and when there is an interaction between these atoms, and then these energy levels are changed, and they form like a band. And if we have n atoms, and there could be any number of atom, here we are taking n atom, and we know that this n is 10 raised to the power 23 by the mole concept. It is very high. And these are the electrons that will respond to electric field. These are the electrons that will respond to electric field, and they will move according to F equal to QE. And here in this case, the electrons in 3s orbit will respond to electric field for electric conduction. Therefore this band is called the conduction band, and just lower to conduction band known as the valence band. So we have taken the example of sodium, and if we take the example of magnesium, which is also a good conductor and of the electricity. So this 1s2, 2s2, 2p6, 3s2. So here you can see this is also filled. Here in 1s there are 2 electrons, and in 2s there are 2 electrons, and in 2p 6 electrons, and in 3s again 2 electrons. So this should be a insulator. No, it's not, because the we know that after 3s there is 3p, and 3s and 3p are merged. Here 3s and 3p are merged because the band structure is different for different metals. For different materials, for different elements, the band structure is different. So 3s and 3p. So definitely there will be some vacant quantum states. So the electron movement can be there, because in 3p the 6 quantum states will be vacant. 6 quantum states will be vacant. So and the 3s and 3p are overlapping. 3s and 3p are overlapping. So for different atoms you have different kind of energy bands. For solids and for the different atom we have different kind of energy bands. And here you can see the 3s and 3p are merged, so they are not separate. 3s and 3p are not separate.